Hello friends, welcome you all. In last lecture, we have discussed the use of IS 456 2000, then different sections in IS 456 2000, then different grades of steel, that is Fe 250, Fe 415 and Fe 500, then the various advantages of steel as a reinforcement, then definition of limit state, then different types of limit state, that is limit state of collapse and limit state of serviceability, then characteristics values, that is characteristic strength and characteristic load. Now in this lecture we are going to discuss the partial safety factor. Okay, so what is meant by partial safety factor? The safety of the structure depends load and the material strength, which are not the function of each other. Hence, two different factors, one for load and the other for material strength, are used. Because each of these two safety factors contribute partially to safety, they are termed as partial safety factors. That is, these two factors, that is load and material strength, are responsible for the safety of the structure. For therefore, these two safety factors contribute partially for the safety. We are termed as a partial safety factors. So let us see first partial safety factor for material strength. So for material strength, it is introduced to account for the constructional faults, okay, or bad workmanship and supervision, or we can say the interior material. So the design strength is obtained by the dividing the characteristic strength by the partial safety factor of the material strength, or we can define as it is the strength reduction factor that is greater than unity when applied to the characteristic strength gives a strength known as design strength, that is Fd is equal to F upon gamma m. Okay, or we can also define as the design strength is obtained by dividing the characteristic strength by the partial safety factor of the material. We can call it as partial safety for material strength. Okay, so where Fd is design strength, F is characteristic strength, and gamma m is the partial safety factor for material strength. Here in this table we can see the material, that is concrete and steel, and the different partial safety factors for limit state of collapse, deflection and cracking. So for material concrete, limit state of collapse, the partial safety factor is 1.5. In deflection it is 1, and in cracking it is 1.3. And material, that is steel, the limit state collapse partial safety factor is 1.15, in deflection 1, and cracking also 1. These two factors, that is for limit state of collapse for concrete is 1.5 and for steel it is 1.15. It is very much important. Okay, so next is the partial safety factor for load. Okay, so the partial safety factor of load, which when multiplied by the characteristics loads gives the design load, or we can define it is the load enhancing factor that is greater than unity, which when multiplied to the characteristic load gives a load known as design load, for which structure is to be designed. Here we can see characteristics characteristic load is equal to partial safety factor for load multiply by characteristic load. Okay, that is Fd is design load, F is characteristic load, and gamma F is the partial safety factor for load. So these partial safety factor taken into account the variations in loads, okay, due to unforeseen increase in load, construction inaccuracies, different loading combination, then secondary effect and type of limit state. Okay, so the value of material strength, that is sorry, the value of partial safety factor for loads, that is as per IS 456 2000, are given in this table. You can see, okay, that is clause number 18.2.3.1 or 36.4.1. Okay, so these uh, partial safety factor for load, that is here we can see the various load combination, that is dead load plus live load or imposed load, dead load plus wind load, dead load plus live load plus wind load, and the various partial safety factor for limit state of collapse and limit state of serviceability. So for dead load plus live load, in limit state collapse this value is 1.5, that is partial safety factor for load, that is gamma f 1.5, and for wind load it is 1. Then dead load plus wind load, it is taken as 1.5 for dead load plus, sorry, dead wind load. Okay, and for dead load plus live load plus wind load it is taken as generally 1.2, and for the limit state of serviceability it is nearly equal to 1. Okay, for dead load plus dead load or live load or wind load also. Okay, so next point is the different types of loads which are act on the concrete structure. Okay, here it is steel structure is given, but it is now concrete structure. So first is the dead load. Okay, so this dead load we are referring the IS code IS 875 part 1 1987. Okay, for all the structure are designed for the worst combination of dead load and live load, or okay, superimposed load we can say. Okay, that is wind load and seismic load are also considered in design wherever applicable. Okay, so first is this dead load, that is we are referring the IS 875 part 1 1987. So what is this IS code? Let us see. Okay, here we can see the IS code, that is code of practice for design loads, that is other than earthquake load. IS 875 part 1 1987. Okay, this is the second revision. This part 1 is for dead load. In dead load, that is unit weight of building material and stored material. So here we can see the IS 875 part 1 1987. Okay, for dead load. So here we can see the scope of this IS code. This code, that is part 1, covers the unit weight mass of material and parts or components in a building that apply to the determination of dead load in design of building. And here we can see the different building materials for which unit weight of building material is given in kilonewton and kg also. Okay, different building materials given. Okay, so this is IS 875 part 1 1987 for dead load. Okay, so next is the live load. For live load we are referring IS 875 part 2 1987. Okay, so let us see this IS code. Okay, here we can see the IS 875 part 2 1987, that is for imposed load, or we can say live load. Okay, so here we can see the scope of this IS code. Okay, so this standard covers the imposed load, that is live load to be assumed in the design of building. The imposed load specified herein are minimum loads which should be taken into consideration for the purpose structural safety of building. Okay, and the according to the occupancy, the different buildings are classified, that is assembly building or business building, office building, educational building, industrial building, institutional building. Okay, then storage building. For these different buildings we are taken the different imposed load on floors. Okay, that is according to the occupancy. And here we can see the different occupancy classification, that is residential building. For that residential building, uniformly distributed load and the concentrated load we are taken. Okay, so this is IS 875 part 2 1987 for live load or imposed load. Okay, next is the wind load. Okay, for that purpose we are referring the IS 875 part 3 1987. So let us see IS 875 part 3 for wind load. Okay, here we can see the IS code. Okay, that is part 3 wind load. So in this IS code, scope of this IS code, let us see what is the scope. This standard gives the wind forces and their effect, that is static and dynamic, that should be taken into account when designing building structures and components thereof. So for designing the buildings for dead load, live load, wind load, we are referring these IS codes. Okay. So for wind load, here different terminologies given for uh, some purpose, that is for some definition given which we should know. Okay, and here we can see the design wind speed we are calculating using the formula Vz is equal to Vb into K1 into K2 into K3. That is, these three are different factors which we can calculate. Okay, so this is for the wind load. Okay, next is for snow load. For that purpose we are referring the IS 875 part 4 1987. So let us see this IS code. Okay, here we can see this IS code for snow load. So what is the scope of this IS code? Let us see. So this standard deals with the snow load on roof of buildings. Roof should be designed for the actual load due to the snow or for the imposed load specified in part 2. Okay, imposed load whichever is more severe. So here you can see the different roof, flat roofs given. Okay, pitch roof is given, and for that the different specifications is given in this IS code. Okay, and last one is the earthquake load. Okay, that is we are referring for that IS 1893 2002. Okay, so let us see this IS code also. So actually this IS code 1893 again divided into 5, that is part 1, part 2, part 3, part 4 and part 5. In that part 1 is the general provision and building. Okay, for that is earthquake resistance structure, criteria for earthquake resistance design of structure. Okay, so in this here we can see the part 1 for general provision and building, part 2 for liquid retaining tanks or elevated and ground supported, part 3 for bridge and retaining walls, and part 4 for industrial structure including stack like structure, that is chimney, and part 5 that is dams and embankment. Okay, so here we can see the actually uh, before the fifth revision there was a 5 zones for the earthquake. Okay, in fifth revision it is first and second is merged, so now only 4 zones is there, that is zone 2, zone 3, zone 4 and zone 5. And according to the region, that is here you can see the map. Okay, map of India for seismic zone of India. Okay, so according to these regions we are designed for the earthquake loads. Okay, suppose our locality in this yellow zone, so that is zone number 3, so we are looking for the different criteria regarding to the zone 3 from this IS code, and we have to design the earthquake load resistance structure. Okay, so this is all about the today's session. Hope you will understand today's session. Okay, thank you.